So what we've been talking about is what is called the method of Lagrange multipliers. So remember, the idea is that you have some function f that you want to optimize, right? You want to find the max or minimum of that function. And you have some function g that forms a constraint. In particular, g is set equal to some constant. So this is your constraint function. We know that you've got to move perpendicular to the gradient of g, or otherwise you're going to leave the level set, right? And then we know that if you want to increase f, you've got to move in the direction of f. So once you get to a point where the gradient, you've got to move in the direction of gradient of f, sorry. So once you get to a point where the gradient of f is aligned with, either parallel or anti-parallel to the gradient of g, then you're at a place where you can't increase or decrease f anymore without moving in the direction that would take you off of the level set, that would move you off of the constraint, and you have to stay on the constraint. So what you do basically, let's see, the way this is set up, they have it set up so that the constraint is of the form g of xyz equals 0. Of course, you could have any constant here, and the gradient of g would still be the same, right? Because we don't care about the gradient of that constant. So, all right. So what we do is we just check this condition. We figure out where is the gradient aligned with, so a scalar multiple of the gradient of g. Let's work an example. All right, we want to find the points on this curve, xy squared equals 54, that are nearest to the origin. Okay, so I can see what my function g is. So g is equal to xy squared, right? And we're trying to figure out where our constraint is that g of xy always has to equal 54. You could do it a different way too. You could call g, maybe I'll call it g tilde. This is another way to describe g. You could say g is the function xy squared minus 54, and like the description before of the method of Lagrange multipliers, you're looking for where is g tilde equal to 0. Either way, if you use this for g or you use that for g, the only difference is a constant, and so the gradient of this g and the gradient of g tilde are the same. It doesn't matter if you use xy squared or xy squared minus 54. The only difference is whether you have a non-zero constant on the right hand side or 0 on the right hand side. Okay. Anyway, we've got our constraint function, and so we know that g of xy is equal to 54, and this is the function that we're talking about. So we've got g. Now we need to find the function that we want to optimize, and this takes a little bit of reading. It says find the points on this curve that are nearest the origin. Well, how do you measure distance from the origin? Well, the distance between any 2 points, right, would be the square root of, let's see, x minus the starting point here and y minus the starting point squared. Okay, so really the distance is going to be the square root of x squared plus y squared. Now, just for convenience, rather than letting this be my function f, I could let this be my function f. I'm going to let f of xy be x squared plus y squared. My reasoning is, if I minimize x squared plus y squared, then the square root of x squared plus y squared will be as small as possible, right? Since the square root preserves the order of numbers, right? The smaller the number, the smaller the square root. So I might as well minimize this. And the reason that that would be better is because derivatives of this thing with the square root involve square roots in the denominator, and they're a little bit of a pain to work with. Not undoable, but certainly easier to work with this function because the derivatives are this is a simple polynomial, right? So the derivatives are really, really nice. All right, so what we want to do is calculate the gradient of f, and we'll calculate the gradient of g, and then we'll try to satisfy this condition. We'll try to make the gradient of f be aligned with the gradient of g, right? Some scalar multiple times the gradient of g. So let's see, what is the gradient of f? Well, the partial with respect to x is 2x, the partial with respect to y is 2y. Now for the gradient of g, here's our function g, right? The partial with respect to x is y squared, and the partial with respect to y is that the 2 comes down, so we have 2xy. So what we need to do is to figure out where is 2x 2y equal to some scalar times y squared, and that same scalar times 2xy. This is really 2 equations. 2x has to be equal to lambda y squared, and 2y has to be equal to 2 lambda xy. We have a system of 2 equations, but there are three unknowns, x and y, and this scalar lambda. So we're going to need one more equation, or we're not going to have the hope to find all three of those unknowns. Well, we can always use our constraint, right, as our third equation, because our constraint also has to be satisfied. We know that xy squared has always got to be equal to 54. All right. Well, now we have a system of three equations and three unknowns, and we need to solve this for x, y, and lambda. Now, one thing that we could do is solve one of these equations for lambda and then substitute that into the other equation. So once I know lambda, I can substitute into that other equation. Let's see. According to the first equation, lambda is 2x over y squared. That would work really well as long as y is not 0, huh? So either that, or maybe I should make a little note to myself, don't forget, if y equals 0, you've got to do something else in this case. So, okay, so now I know lambda is 2x over y squared if y isn't 0. I can go to this equation which says 2y is equal to 2 lambda. 2 times lambda would actually be 4x over y squared times y squared. Ooh, that's pretty nice. So 2y equals 4x, dividing both sides by 2 tells me y equals 2x. Now I know that y equals 2x. That's an equation that doesn't involve lambda. Here's another equation that doesn't involve lambda. Let me substitute this in. We get x times y squared, but y squared would be 4x squared equals 54. So 4x cubed equals 54. So let's see. So x cubed is equal to 54 over 4. That would be 27 over 2. So x is going to be the cube root of that, right? Which would be 3 over the cube root of 2. Once I know x, I can go and pick up y from this equation. Y is 2x, so y is going to be 6 over the cube root of 2. There was one possibility that I should consider, though. It's not really fair to divide both sides by y squared if y is 0. So if y is 0, then in this equation, if y is 0, that says that 2x has to be 0. So there's also a possibility that y could be 0 and x could be 0. And so those are two solutions to our system of equations. Oops, except for this won't work. If y is 0 and x is 0, if we try to take xy squared, it would be impossible for us to get 54. We can eliminate this one then. Nice. Okay. So what we need to do then is to figure out, is this a max? Well, let's see. We actually know that there is no max for this, right? No max for the distance from the origin. You could just keep moving out further and further in the x or the y direction. You could make x really small and you could get y really big, so you could get really, really far from the origin. So there is no point that's furthest from the origin, but this would be the point where we are closest to the origin. So here's the point, right? Here's our solution. 3 over the cube root of 2 and 6 over the cube root of 2.